Alright, so welcome back to particle physics and a standard model. This is lecture 9, and last time around we saw how CP violation was actually measured in the weak interactions, right, using K-on systems. We wrote the K0 and the K0 bar in terms of CP eigenstates, and then if CP were conserved, we saw that one of those eigenstates would go to 2 pions because it's a CP even eigenstate, the other one is a CP odd eigenstate that would go to 3 pions. So if you prepared a beam of the K0 state, then nearby you expect lots of 2 pions, and then far away you expect to get only 3 pions, right. However, there was a contamination seen far away of the 2 pi final state, and that signaled that there was CP violation, and we parameterized the amount of CP violation with an epsilon and said that in the weak interactions CP violation occurs at the level of 10 power minus 3, right. I told you last time that we will explore one other fun consequence of having this CP violation in the weak sector, right. So this fun consequence will teach us some very interesting physics, okay. It's not very rigorous physics, but it teaches you something very interesting. The idea is this, okay. Could you ever communicate to, let's say, an alien species, okay, let us say we are encountering some extraterrestrial species, or we are sending signals, we are not encountering them physically yet, we are sending signals to an extraterrestrial species there in their spaceship or planet or whatever. Is there some way in which we could communicate to the species what we mean by the concepts of right and left, okay? How could we ever do this before meeting them, right? Now among us in the human civilization, we know this by convention, we have been seeing this all our lives, so we automatically know what is right and what is left, correct. But in a physical sense, how would you describe this to an unknown civilization? This is where CP violation comes in, okay. How is that? Now assuming that they also know, they have also done a lot of particle physics experiments, they have also seen CP violation, okay, that is at that level of intelligence we will grant them. If that is the case, what we can ask them to do is, they would also know how to prepare eigenstates, right, and we saw that after we knew there was CP violation, we could now write K0 and K0 bar in terms of K long and K short eigenstates, correct. So what was K long? K long was the linear combination of K2 and K1, where K2 is the CP even or CP odd rather eigenstate, and K1 was a CP even eigenstate that we had written down before, correct. Why is this K long? That is because this is the one that goes to the 3 pions, right, this is the longer lived state. And similarly K short we had written as this, right, just to jog your memory. Good. This is the sensible set of eigenstates that we can work with, right. So we tell them to prepare the K long eigenstate, we tell them to actually work in this eigenbasis, and we tell them that K long in K long, right, it decays to 3 pions, right, it actually decays to this state. We can ask them to take we still do not know how to tell them what is positive and what is negative either, remember, right? Positive and negative are also human conventions, right? So how can we even distinguish between these two also? So we tell them, take the final state that is a little more preferred by this reaction. What do I mean by that? So you have the pion going to a positron and an antineutrino, the positive pion, the positively charged pion, and the negatively charged pion goes to an electron and neutrino, correct? Okay. Now because of CP violation, you will find that E plus is more preferred than E minus, at a 0.1% level, 10 power minus 3 level again, right? Okay. So what we tell them is, take the final state, take the leptonic final state that is more preferred in this decay process. Okay, we do not know how to specify it as plus or whatever, right? Now, okay, once we say this, they will pick the E plus, right? Good. And then we define right in the following manner. Okay, we say whatever lepton you got in produced in the decay of pions, right? You take that and check for the helicity of this lepton. Okay, now we know that this positron has to have right helicity because it is a weak interaction, right? So we know that the positron here is right handed, correct? Okay. So now it's going to be easy to define what right is, right? Because we can now use gravity. We just tell them to go stand on a plane surface, okay, and then we tell them that above your head is up, down, below you is down, obviously, right? So up and down are easy to define because gravity will define that for you, right? So that is intuitive, that can be easily conveyed. But we still do not have right and left, but what we tell them is, you take this lepton plus or minus whatever, they will pick a plus, they will pick the plus, right, they will pick the positron and look for the helicity and see in what direction the spin is aligned, right. Since it is right handed, you tell them that, so so you tell them, you look for the helicity and assume that the spin is aligned up, right. And then if it is right handed, you tell them it goes from either there is a direction in which the spin goes from behind you to above you, right. And if it is right handed, the direction that your hand or appendage or whatever should sweep as it goes from behind you to the front of you, that is right. You use helicity basically, corkscrew argument. If it was left handed, it would have been this way, right, the positron that they would have picked would have been this way, it would actually have been the electron, and then you say that the direction in which your appendage sweeps from behind you to front of you would have been in this direction, right. So that would have been left. Okay, so I think this is a neat little mental exercise to think about. There is a lot of assumptions about our coordinate system that we take for granted, and things like C and P and discrete symmetries help us resolve these deeply seated assumptions that we have. Okay. Alright, so you can look at this argument in little more detail. You can, I think Feynman gave a very similar argument in one of his lectures, I guess in his messenger lectures, but you can also look at this in Griffiths. I believe he gives this as a homework problem. Okay, Griffiths elementary particles. Alright. So with that, let us close our discussion on CP, and move on to the one discrete symmetry that we haven't talked about yet, which is time reversal or T, denoted by T. Okay. So, what is time reversal? I think I mentioned this in one of the earlier lectures. You just run the video backwards, right? You just flip the direction of time at a microscopic level and see what happens. T goes to minus T. The time coordinate flips. Okay, what happens under this? That is the operation. So, before we get into what happens at the fundamental level, let us think for a second about classical mechanics, okay, at the macroscopic level, right. If you have not heard of this question before, I think now is the time to think about it. In classical mechanics, right, with Newtonian dynamics, which is the basis of classical mechanics, right, F is equal to ma, and then you have the universal law of gravitation and things like that. There is no arrow of time in those equations, correct, right. So, if I write F equals ma, under time reversal I get back the same equation, correct. Similarly, let me just write Newton's universal law of gravitation. Again, no arrow of time. I flip time, nothing happens to this nothing happens in the equations, right. And yet in the classical world, in the macroscopic world, we do definitely see an arrow of time, right. Everything hot gases diffuse, they don't they don't return, there is no recurrence that you see in normal time scales, right. Entropy seems to be increasing all the time. So, how is it that in the equations that govern classical mechanics, there is no preference for a direction of time, but all the phenomena seem to have this direction of time. So, if somebody has not asked this question to you before, now is the time to think about it. You can pause and think about it, or you can look it up and think about it, okay. But I will just tell you the answer now. The answer is initial conditions, okay. It is the way you set the initial conditions that set the arrow of time. So, to take the gas example, you put gas in a box, that sets the initial condition, that sets the initial entropy, and then you heat it up or you just release it, the gas diffuses away, right. You open the box, the gas diffuses away. Not because it is baked into the equations, as because the initial conditions that you set were such that the evolution through these equations gives you a sense of the arrow of time, okay. Very good. Boundary conditions. Okay. Now, for parity and charge conjugation, we talked about the intrinsic parity and charge conjugation for various states, right. In other words, we looked at what qualifies as an eigenstate of C and an eigenstate of P, right. So, now that begs the obvious question, are there eigenstates of time reversal? Could there be? No, the answer is no, okay, and it is an intuitive answer, all right. The intuition is that see, a state can be its own mirror image, right. You can intuitively think about this, right. In a mirror, a state, you can actually imagine that the state can be its own mirror image. A photon in the mirror would look the same, it would interact the same, right. And similarly, one can imagine that a particle state can be its own antiparticle state. A photon is its own antiparticle, right. A neutral pion is its own antiparticle. These things can be actually physically manifested, but if you time reverse a state, right, it cannot be itself, it cannot be its own, it cannot be identical to itself actually, right. It cannot be its own Benjamin button, so to speak, right. A particle moving forward in time is a definite state, The same particle, imagining it moving backward in time, is not identical to the original state that you are thinking of, right. So really there are no T eigenstates to speak of, unlike P and C. Okay, you can apply the time reversal operator, but no, there are no eigenstates. Okay, that's something important to understand. However, you can still check whether a certain theory, whether a certain set of interactions like the weak interactions or electromagnetism or strong interactions are still invariant under this transformation of time reversal. Okay, time reversal can still give you some state. Let's just name it that. You can transform the state under time reversal and check whether this transformation still gives you a theory that is invariant under this operation. Okay. So now let us look at some observational aspects of this. It turns out time reversal is a testable thing in the strong interactions. Okay, so let us write that. So time reversal is testable in strong interactions. How is that? Let me write a sort of a famous strong mediated process, which is deuterium formation. Okay, you see this in many contexts. This is what happens in stars in a very temporary way. This happens in the early universe in Big Bang nucleosynthesis. This is how you get all the deuterium in the universe. Okay, and this is mediated by the strong interactions. And how do you test it? You check the rates on both sides. Okay, the forward rate you find is equal to the backward rate. Okay, what is this called in physics? If you have done thermodynamics, if you have taken a course in thermodynamics or statistical physics, this is called detailed balance, right. Under equilibrium conditions, these two rates are seen to be equal. That tells you that in the strong interactions, time reversal is a good symmetry. Okay, but can we test this in this direct way by just looking at processes? Can we test this in the weak interactions? Turns out it is very hard, so hard that people have not really done it. Okay, why is that? Let us take an example. Okay, so let me just write here, this is for strong. What about the weak interactions? The quintessential weak interaction is beta decay, neutrons going to a neutron decaying to a proton, electron, and an electron and a neutrino, right. Why is this so hard? That is because you can actually control neutrons. Okay, you can actually bottle neutrons. Okay, you can even make them ultra cold. By ultra cold I mean they become so using magnetic fields and things like that, you can slow them down and control them and slow them down and make them so slow that you can even outrun them. Okay, you can actually jog faster than them. So you can just make neutrons a few meters per second, put them in a bottle, and so you can actually observe the forward reaction. Okay, but it is not possible, it is not so easy, so it is tough to measure the backward reaction. Why? Because you can't control neutrinos so easily, right. Protons and electrons probably, yes, very well. We have colliders for protons and electrons, accelerators and so on. But how do you control neutrinos? You can create some neutrino beams, but that does not necessarily mean you can put these three particle species together and actually measure the backward reaction of them going back to a neutron, for instance, right. So not only that, you expect the weak interactions to give you very tiny signals, by which I mean small event rates that in turn come from small event counts that just basically come from the suppression of rates of processes from very weak coupling strengths. Okay, what are coupling strengths? So we will encounter all this. There is a reason why the weak interaction is called the weak interaction, okay, because it's a very feeble interaction, so you don't interact enough and produce large enough rates, okay, in particle processes. Okay, so you are hampered by all this, and it is very hard to test time reversal in weak interactions. Okay. Now you might wonder, what if I do not have neutrinos, what if I look at other processes. Okay. So for example, you can have the lambda baryon decaying to a proton and a pion. This is mediated by the weak interaction. But even this is hard to control, and the reason is the reverse reaction where you have pions and the proton combining to give lambda, right, that is swamped by QCD backgrounds. So if you take a meson and a proton and smash them together, you are going to have a lot of quarks and gluons coming out that would confine to give you more mesons and hadrons. So it's like searching for a needle in a haystack basically. Okay, to single out just the lambda baryon from this would be very hard. The strong interactions are much faster anyway, there will be more events from them, so this will be buried under those. Okay, so there are many such difficulties in testing for time reversal in weak interactions directly. Okay, so what can we do then to test time reversal? Well, one thing you can do is, we touched on this a bit before also, is to make use of electric dipole moments. Okay, that is what we use to test time reversal. Why is that? Well, here is why. Okay, so if you measure non-zero electric dipole moment, okay, for any particle state, then that implies that the interactions in which it participates violates time reversal. Okay, but so far we have not really measured a non-zero electric dipole moment. For the electron, people have tried to measure, and then they could not, they only set an upper bound. For the neutron, we saw last time it was around this, right. So far we have not really seen this, and so we know that the strong interactions or electromagnetism does not violate T. But again, how do we know that the electric dipole moment is what gives you a measure of the violation of time reversal? So think about it this way. Okay, so the EDM, the electric dipole moment, is a vector, right, and let us say that for a given particle state, the dipole moment, electric dipole moment, points in this direction. Okay, and then let us say that for the same state, the spin of that particle, okay, points also in the same direction. Okay, let's take this basis for now. Okay, and this need not be just the spin, it could also be the magnetic moment, right, the magnetic dipole moment, correct, they have the same alignment, right. Okay. Now this is what I am defining as my state, right. Okay. Now suppose I put this under time reversal, what happens? In that case, will the spin flip or not? It will, right, the spin will flip, right. So spin is a very quantum mechanical thing, but for this analogy, for this illustration, think of it as a classical spin, right. So a spin basically means what? It means so if I have it in this direction, it means it's literally like spinning in this direction, right. That means under time reversal I would basically flip the direction of the spin, that means it would point in this direction, right. So that is what happens to the spin or the magnetic moment, but the electric dipole moment is a more trivial thing, right. It is just the vector direction or the vector distance from the positive charge to the negative charge in any charge separation possible within a particle state, right. Because of that, there is really nothing happening under time reversal, correct. The actual electric dipole moment still remains the same, it has not flipped, right. So there you go, under time reversal I have changed how the particle state looks like, right. I have flipped the spin, but not the electric dipole moment, right. So that tells you that if you do measure a non-zero electric dipole moment, then the whole the entire state and its interactions violate time reversal symmetry, okay. This is how we know that in the strong interactions we saw the strong CP problem, right. By measuring the neutron EDM, we saw that in the strong interactions you expect large CP violation, but you get a level of CP violation consistent with 0, right. So what they actually measured was not really the CP violation, they actually directly measured the time reversal property of this, okay. And we know that under the CPT theorem, if you violate CP, then you violate T, right, because CPT is conserved, okay. Very good. So we are done with discrete symmetries and we are going to segue to continuous symmetries, all right. So in the last 2 or 3 minutes of this lecture, let me give you a little refresher on continuous symmetries and then we will take it up further, okay. All right. So can you name some continuous symmetries? Let me start a new page for this. Right. So we saw CPT were some discrete symmetries. There is already some continuous symmetries we talked about even in the very first lecture, right. So we have time translation, correct. If this is a transformation, but if your theory satisfies this, then time translation is a symmetry of the theory as well, right. We also had that, correct, space translation, space time translation if you will together. Galilean boosts and corresponding Lorentz boosts, correct. Rotations and so on, right. Okay. So good. So hopefully now you get an idea of what we mean by continuous symmetries. These we will now apply in the, some of these at least we will now apply in the quantum realm, okay. And in the next lecture we will take up rotations and hence the concept of angular momentum, spin and so on, alright. Okay. So we will pick that up in the next lecture. Thank you.